This next section contains a brief review of some of the key specifications for point-to-point microwave systems. Point-to-point microwave systems today use quadrature amplitude modulation, or QAM, sometimes pronounced QAM or QAM. The basics important to point-to-point capacity are shown in this slide. The figure shows a constellation plot for 16 QAM. You can see that 4 bits are used to describe one symbol in this 16-symbol array. In this case, the L factor is 4. Each symbol has a unique amplitude and phase associated with it, and these are constructed with an in-phase and quadrature phase symbol that is 2 bits in length for each. The figure is showing that impairments in the transmission of the signal can cause impairments in the associated symbol, reducing its decision distance and potentially causing an error. As channel impairments increase, such as distance of transmission, lower power transmitters, or amount of noise, for example, the amount of impairments that reach the receiver increase, and an error is more likely to occur. The red squares describe the decision area around a given symbol. If the actual received symbol plus the channel impairments exceed the red boundary, an error will occur. As I described earlier, the need to increase data throughput in point-to-point systems is large and ever increasing. Therefore, operators and equipment makers are working hard to increase the number of bits per symbol that can be transmitted in a given bandwidth. One way to do this is to increase the modulation depth. On the left side of the slide is an example given for increasing the level of QAM used in a given bandwidth. When QPSK is used, the number of bits per symbol is only 2, and the constellation would just show 4 points, one in each of the 4 quadrants illustrated. When the modulation level is increased to 16 QAM, L goes from 2 to 4, and the corresponding channel capacity is doubled. The signal now transmits 4 bits per symbol per unit bandwidth, as opposed to 2 bits per symbol per unit bandwidth with QPSK. The trade-off is that the decision distance from one symbol to the next is reduced twice, therefore requiring 6 dBm more signal-to-noise ratio in order to correctly receive the signal. The example shows that as a modulation depth is increased, the amount of extra capacity achieved is less and less, showing diminishing returns after a point due to the continued requirement of 6 dB more signal-to-noise ratio for each modulation step. Additionally, as the modulation depth is increased to levels like 1024 QAM, or also called 1K QAM, and 4K QAM, the resulting signal becomes more sensitive to other system-level impairments, like group delay and phase noise, which causes phase shifts in the constellation. The higher order modulation also has a higher peak-to-average power ratio, requiring higher amounts of backoff at the power amplifier or means to correct for distortion like digital pre-distortion, both of which cost extra power or hardware or possibly both. In many cases, though, when no other options exist, such as the case with fixed frequency allocations in the traditional microwave bands, the only way to increase capacity while remaining compatible to the system is to increase the modulation depth, but it comes at a cost. To a limit, this method is used today in many microwave systems, and high-performance gigasample per second converters are enabling systems to be designed with higher order modulation like 1K and 4K QAM. Many systems will increase or decrease the modulation depth to adapt to the changing channel conditions to maintain an acceptable amount of SNR. This, however, will directly affect the amount of capacity and throughput the system can provide. Another concept to understand in point-to-point systems is the notion of channel spacing versus channel bandwidth, or symbol rate, sometimes called baud rate. The figure illustrates the differences between them. A point-to-point system, channel spacing is normally allocated by a governing body through licensing. So-called traditional or legacy band allocations range from as narrow as 3.5 MHz up to 112 MHz. In the case of the new E-band, the allocations are given in 250 MHz chunks and can be up to 1 or 2 GHz, 4 or 8 sections of 250 MHz. These allocations are fixed for a given deployment. Signal bandwidth, on the other hand, is determined by the equipment. For inter-symbol, interference-free, or ISI-free data transmission, A special class of channel filters known as raised cosine filters are commonly used. These filters have unique properties that minimize the amount of excess bandwidth needed to implement them, while also having the property that all zero crossings in the time domain happen on symbol boundaries. Thus, no symbol interferes with its neighbor, hence the name ISI-free filters. The raised cosine filter can be considered a practical implementation of the ideal brick wall filter, while limiting the pulse response to a finite length in the time domain. This is done by means of the roll-off factor, given as the beta term in these slides. The higher the beta in the range of 0 to 1, the more excess bandwidth is used, but the shorter the pulse response of the filter. Since bandwidth is a premium in point-to-point systems, the beta factor is small at 0.12, reducing the amount of excess bandwidth to as little as possible while still allowing a filter design that's practical to implement. This example shows the case of a particular system that is designed with a roll-off factor of 0.12. For a 56 MHz channel spacing system, the maximum achievable symbol rate for that system is 50 megasymbols per second. An additional way to achieve higher capacity, other than increasing modulation density or using wider bandwidth, is to utilize cross-polarization techniques. There are a few different techniques that can be implemented in these cross-pick or X-pick systems. For an adjacent channel copolarization system, these radios have the same polarization as each other, but operate in separate adjacent channel bands or frequencies. The second radio is used for redundancy or can be used to gain capacity at a different operating frequency. However, this requires two different antennas, as they are operating at different frequencies, as well as additional frequency allocations, which can be costly. Adjacent channel alternate polarization utilizes two different frequencies like the copolarization scheme. However, the second radio is polarized to an orthogonal phase from the first radio to minimize the interference between the two channels. This system, however, still requires two antennas and two frequency allocations, which is additional cost and design overhead. The more efficient scheme is the co-channel dual polarization system. For this configuration, both radios are operating at the same frequency, but have different cross-polarizations for minimizing the co-channel interference. In this setup, only one antenna is needed as both radios are operating on the same frequency, minimizing system costs. Ideally, for this configuration, if the polarization was completely orthogonal, it would mean both channels are completely isolated from one another. In reality, though, it is difficult to achieve greater than 25 dB of isolation between the two polarizations due to either varying weather conditions and other environmental factors that may cause link degradation. However, since the two radios share the same received signal, it is possible to use digital processing for interference cancellation of these cross-polarized signals in the modem algorithm and can correct these interference signals. This is another way to double the capacity of a system and also minimize cost by reducing hardware and using additional digital signal processing as an advantage. When all of these considerations mentioned so far are taken into account, an estimate of the capacity can be made. In this slide, some calculations of raw capacity for various links are shown. You can see that the traditional band radio can achieve quite a high raw capacity, but it is using many of the advanced techniques discussed in this presentation, like the likelihood of additional capacity gain is very low. The new E-band system, on the other hand, delivers more than 50% higher raw capacity than the optimized cross-pick traditional band system, with a relatively low complexity modulation. The key is the 500 megahertz of bandwidth in the allocation. You can see that there is much more room to grow in raw capacity as E-band radios become more capable. The actual payload or throughput of these systems, however, is lower than the raw capacity, and it is dependent on a number of factors. Forward error correction can be a big one, sometimes consuming as much as 50% of the raw capacity in the case of long distances or difficult radio transmission environments. There is an overhead of about 5% from network data management, but this can be offset by compression of the data or the traffic headers or both. The high raw throughput of the new E-band systems offers clear advantages for increasing backhaul throughput to 10 gigabit per second or more. And as I'll discuss next, wideband gigasample per second converters are enablers for those systems.